Welcome, everyone. Today, what we're going to be doing is a remote video lecture for wrapping up Chapter 3, which was on stoichiometry. And then we're going to get started on the first half of Chapter 4, which is reactions and solutions. So the last thing we needed to pick up from last class was the final question from Chapter 3. So let me share my screen here. And we'll go to presentation space. Okay, here we go. So the question we left off with was this one. So methanol is the simplest alcohol. It's used as a fuel in race cars and is a potential replacement for gasoline. Methanol can be manufactured by combining gaseous carbon monoxide and molecular hydrogen. Shown below is the balanced chemical equation. And so here's the balanced chemical equation. And then in part A, the question says, suppose you have 68.5 kilograms of carbon monoxide and it is reacted with 8.60 kilograms of H2. Calculate the theoretical yield of methanol. So then in part B, the question says if 3.57 times 10 to the 4 grams of methanol is actually produced, what is the percent yield of methanol? So to solve this question, what we need to do is we need to assume that we have our amount of H2 and it's going to all get depleted, but we're going to assume that there's an excess of carbon monoxide. So we'll assume that the H2 is what gets depleted, and then that's going to then dictate how much methanol we are going to make. That's going to be one half of the calculation for part A. Then in part B, we're going to say, okay, well, let's assume we have excess H2 and we have a limiting amount of carbon monoxide. How much methanol can I make from that calculation? Then you're going to compare the two numbers. Whichever number is smaller is going for the amount of grams of methanol that you produce. Whatever one is smaller is going to then tell you which one of your reagents is the limiting reagent, and that's going to be how much methanol that you are going to produce. So going into the question here, we're going to start first by assuming H2 is the limiting reagent. And so here we're solving for the mass of methanol, assuming that H2 is the limiting reagent. And so on the question, we are given 8.60 kilograms of H2, okay? And so here's the 8.60 kilograms of H2 that we are given. And what I can do here is I can write it directly into grams because 10 to the positive 3 is kilo. So I have 8.60 kilograms of H2. And then what I can do from there is I can then go from grams of H2 into moles of H2. And the reason I want to go into moles is from the chemical equation, I know that there is a 2 to 1 to 1 mole ratio. So if I want to pivot from H2 to methanol, I need to then get into the unit of moles. And so you'll notice that I get the mass in grams. I then pivot into moles of H2 using the molar mass of H2. And then what I can do here is I can look at the chemical equation and see that there's a 2 to 1 mole ratio of H2 to methanol. And so because there's a 2 to 1 ratio of molecular hydrogen to methanol, I can then cancel out my moles of H2 and now move into moles of methanol. Now that I'm in moles of methanol, I can then look up the periodic table, calculate the molar mass for methanol, and I can then pivot out of grams, or sorry, I can pivot out of moles of methanol and move into grams of methanol. And when I do that calculation, I'll then get an answer of 6.82 times 10 to the 4 grams of methanol. Okay, so that's the first part of this question. So I'm going to assume that H2 is the limiting reagent. So in this part that we did first, we have assumed that carbon monoxide is in excess and that we're going to assume that H2 is the limiting reagent. Now we're diving into the second part of part A. We're going to now do the reverse. We're going to assume that carbon monoxide is the limiting reagent. And so now we're going to assume here that H2 is given in excess. So here we're going to assume carbon monoxide is the limiting reagent. We're going to calculate the mass of methanol, given that CO is the limiting reagent. And so if we go back to our question, we see that we have 68.5 kilograms of carbon monoxide. And so what you'll see here is we start off with 68.5 kilograms of carbon monoxide. You can then look up the molar mass of carbon monoxide. You can then go from grams of carbon monoxide to then moles of carbon monoxide. Then, just like we did in the earlier question, we can then use the molar mass to pivot from moles of carbon monoxide to moles of methanol. And you'll notice here that in the question, it's a 1-to-1 ratio. So we know for every 1 mole of carbon monoxide, we are going to produce 1 mole of methanol. Now we're in the unit of moles of methanol. So then, like the question above, we can then use the molar mass of methanol to then pivot from moles of methanol into grams of methanol. And when you do that, you are going to then get this answer for the amount of methanol produced, assuming you're going to have carbon monoxide be the limiting reagent. There's one thing I want to comment on here. So you'll notice here that in this calculation that we just did, here we have the 1-to-1 mole ratio of methanol to carbon monoxide. So technically, sometimes people will say, do I need to show that step since I'm just multiplying by 1? So it is true that mathematically what you are doing is multiplying by 1 over 1. But what you're doing here is more than just multiplying by 1. You're doing a unit conversion, and you have to have that step to then show how you cancel out of moles of carbon monoxide and move into moles of methanol. So in terms of showing your work and getting the full credit, you need to make sure that you show all the units for the complete calculation. Okay. All right, so that's the first part. And that's actually the harder of the two questions that we're going to be doing. So what we can see now is if we assume H2 is the limiting reagent, we see we're going to be able to make 6.82 times 10 to the 4 grams of methanol. If we assume carbon monoxide is the limiting reagent, we're going to see that we are going to make a little bit more, which is 7.84 times 10 to the 4 grams of methanol. Okay. And so what we can see here is whatever one of these numbers is going to be the smallest, that's going to be the reagent that runs out first. And so we can see here that since we make less H2, we can see here that because we make less methanol from H2 than the amount of methanol we make from carbon monoxide, we can then determine that H2 is the limiting reagent. So because this number is smaller than this number, this tells us that H2 is going to be our limiting reagent. And so now what we can do is we can then go on to part B, which is what is the percent yield of methanol? So the equation to calculate the percent yield is it's going to be percent yield is equal to your actual yield divided by your theoretical yield times 100. And then just remember when you multiply by 100, that turns your number into a percentage. And so the actual yield is from the question, which is the 3.57 times 10 to the 4 grams of methanol. So that's going to then go in the numerator over here. And then the theoretical yield is what you get by your stoichiometry calculation. And so we know that if the chemistry were to go perfectly, we would only be able to get 6.82 times 10 to the 4 grams of methanol. That's what the chemistry says that we should get. And so that's what we then call your theoretical yield. That's assuming the chemistry goes perfectly. There's nothing that goes wrong. We have 100% efficiency and everything. And so what that's going to do for you is that is what we call our theoretical yield. And so if we then take the ratio of the actual yield and the theoretical yield, you're going to then notice that grams of methanol and grams of methanol will cancel. And then you're left with a unitless number that then you multiply by 100, and then you then get the percentage symbol. And when you do that for this particular question, you're going to then get a percent yield of 52.3%. Okay. And so that's going to be sort of the wrap up of this question here. So what's nice about this question is it really shows the importance of why you need to have a balanced chemical equation because these ratios, the mole to mole ratios, are specific to the balanced chemical equation. And it's necessary when they essentially try and calculate how much of a given product are you going to produce. Okay. And so this is a really common type of calculation, both in introductory chemistry, and then it's one of the major calculations that you'll be doing when you take organic chemistry in the future. Okay, so now that wraps up chapter three. So let me just X out of that. And now we will go to chapter number four. Okay. So chapter number four is going to be on reactions and solutions. This is sort of a hodgepodge chapter. So reactions and solutions are very common and widely used in chemistry. Um, the reason it's a hodgepodge chapter is later on in chemistry 3A and 3B, you'll have a whole chapter on acids and bases. You'll have a whole chapter on oxidation reduction reactions. And so this chapter is meant just to give you a sample of the major types of reactions that we'll be dealing with. And one of the ones that we'll be talking about in this chapter is also what's called a precipitation reaction. So, one thing that's worth pointing out here is you just gotta remark how good how nice and remarkable water is. So, just some information about water. It's polar. It has a molar mass of 18.02 grams per mole. It boils at 100 degrees Celsius, and it has a bent molecular geometry. Okay, so you can see here. Here's our structure of water. And the oxygen hydrogen bond length is 95.84 picometers, where pico is times 10 to the negative 12. And it has a bond angle of about 104.45 degrees. So that is water. Water is special because water is so small, and yet it exists as a liquid at room temperature and under normal atmospheric conditions. And that is insanely beneficial for us because we consume water and we are mostly water as well. And if water don't exist as a liquid in these regular conditions that I'm sitting in my office right now, then we would not exist as the way we are. So water is very important. And it's just worthwhile to note that most other molecules that are similar in size, methane, carbon dioxide, carbon monoxide, those are all gases at regular room conditions. Okay. But water is not. Water is going to be a liquid, and so water is really special in that sense. And that's a theme you'll see as you take, multiple chemistry classes. All right. So the reason we're talking about water here is we're going to talk about solutions. Okay. So for example, let's say I have some salt, some sodium chloride, and I then put it into some water. That's going to then give me a salt solution or a sodium chloride solution. And so in this case, the solute is going to be then the sodium chloride, which is going to be dispersed among the water. And then the water is then going to be what's called then the solvent. It then solvates the solute. And then collectively, the solute plus the solvent, or the sodium chloride plus the water, is then collectively called then the solution. Okay? And as you know, throwing sodium chloride in water, the sodium chloride dissolves very readily. You can also do the same thing with table sugar, which is molecularly called sucrose. So you can put table sugar or sucrose in water and it will dissolve. And so, certain solutes will dissolve in certain liquids. But predicting that is actually rather complicated, sort of predicting it from scratch. And so what it sort of boils down into is this question we have up here, which is why do some materials dissolve while others do not? So the analogy I sort of want to give you to sort of consider this is imagine you are watching Netflix at home and let's say it's been raining for a couple days, it's now finally dry, and your lawn is really long, and it's time for you to mow it. Okay. It's going to be hard for you probably to want to go outside and mow the lawn now that the lawn is dry because you have to give up your interaction with Netflix to then have the interaction with the yard work. So in this example, I would gander that most likely the person Netflix interaction is going to be stronger than the person yard work interaction. And so in this circumstance, hypothetical as it is, you're probably not going to put down the Netflix remote and the lawn will remain unmowed. Okay. So this is our little analogy describing why you're going to stay with the Netflix. Does that mean you're going to stay with Netflix forever? No, it does not. So let's say, for example, your neighbor is hosting an awesome dessert buffet. And now you're like, okay, well, I could go to the dessert buffet, or I could stay watching Netflix alone with lousy snacks. And so, probably in that case, you would then put down the remote and then go over to your neighbor's place and then score on some amazing desserts. And the reason you put down the Netflix remote is because your person dessert buffet interaction is stronger than your person Netflix interaction. Okay. So the person Netflix interaction has not changed from this example to this example, but it is being compared with a different interaction, which is the interaction of you doing yard work or the interaction of you then consuming lovely treats at a dessert buffet. And so that essentially is the main concept behind why some solutes will dissolve or why some compounds will dissolve while other ones will not. So when you have a solvent such as water and water, and you then have a solute, which is what's dissolved in the solvent, such as sodium cation and chloride anion, those are our solutes, you're going to have a mixture of interactions. So first off, we know that there is going to be a solvent-solvent attraction. As you will learn later in this class and might have seen in an earlier class, water likes to interact with itself via hydrogen bonds. We also know that sodium cation and chloride anion, they like to interact with each other via an ionic bond. So there exists solvent-solvent attraction and there exists solute-solute attraction. To get the sodium chloride to dissolve in the water, we have to overcome that solute-solute attraction and that solvent-solvent attraction to then favor having what's called an solvent-solute attraction. So we need to have attraction between water molecule and the sodium cation, and we need to then have attraction between the water molecule and the chloride anion. And what you can see here is that red atoms are oxygen. So you'll notice here we have the red atom for oxygen in the water molecule. It's going to have a partial negative charge on it because oxygen is a lot more electronegative than hydrogen. So this little lowercase delta is going to represent a partial negative charge. So there's going to be partial negative charge character on this oxygen, and that is going to be attracted to the full-on positive charge of the sodium cation. Conversely, because the oxygen has the partial negative on it, that's going to put a partial positive on the hydrogen. And so since it's a partial positive on the hydrogen, that means the chloride anion, the negative charge is going to be attracted to the positive charge of the water. Okay. And so for us to break up the solvent-solvent attraction and the solute-solute attraction, when we then pour in the sodium chloride into the water, we then have to then favor something else that is attractive, and that's going to be the solvent-solute attraction. So that's one part of the story. The other part of the story is you'll learn later on in Chemistry 3B that there's this concept called entropy, and the world does tend to favor disorder. And so if you have pure water and pure sodium chloride, you have more disorder if you add the sodium chloride into the water. So that's another contributing factor. But this is just sort of a big overview explanation for why some ionic compounds will dissolve while other ones do not. Okay. To investigate why each particular one is going to dissolve or not dissolve, that's going to require a more detailed analysis. And so there's no really good trend that people can use to sort of make that prediction. And so as a result of that, there are these things that exist which are called solubility tables. And we'll go into that later in today's lecture. But essentially, you use a solubility table to then predict whether or not a particular compound or ionic compound will dissolve in water or not. So, just to sort of show you our little picture here, what does it look like when you actually dissolve sodium chloride in water? Well, you have your sodium chloride crystal, your salt crystal, and it's going to then dissociate into the chloride anion and the sodium cation. And the partial positives on the waters are going to orient themselves around the chloride anion. And then the partial negatives of the waters are going to then orient themselves around then the sodium cation. And so what you can say here is the chloride anion is solvated by the water molecules. And you can look over here and say that the sodium cation is also solvated by the water molecules. And this solvation is due to the solvent-solute attraction that we have. Okay. So this is our big conceptual picture for why some ionic compounds will dissolve while other ones will not. Um, so one thing we'll talk about a little bit is when you're talking about dissolving molecular compounds, things such as ethanol, the way it works is that molecules of similar polarity will interact with other molecules of similar polarity. So for example, here we have, this is the molecule ethanol. So it's, we got two carbon atoms. We then have an OH bond here, and then we have some hydrogen carbon bonds over here. And so, as we'll learn sort of later in this class, the OH group, right? Oxygen is very electronegative. It's going to have a partial negative. And then hydrogen is not that electronegative, so it's going to get a partial positive. Okay. Well, like we talked about in this slide with the solvation of the water molecules with the charged anions, we see here that there's going to be a partial negative on this oxygen for the water molecule, and that's going to then be attracted to then this partial positive on the hydrogen. Okay. And that attraction is going to want to cause the ethanol and the water to interact and mix with one another. Okay. And so, so we'll develop this sort of analysis later on in the class. But the point being is that ethanol and water like to mix with one another because there's a attraction between the two of them. Later on, we'll learn that that's in fact partly hydrogen bonding. But the example to just sort of illustrate why ethanol and water mix really well together is as an example that you might find in the grocery store. Vodka is normally about a 50-50 mixture by volume of ethanol to water, and it appears all as just one single phase. And you don't see like two substances by eye. It's a homogeneous solution. And so that's a grocery store example of this concept in action. All right, so one other thing that your book talks about a little bit is something called an electrolyte versus a non-electrolyte solution. So if you get, for example, sodium chloride, you dump it in water, you're going to then get the picture like we have over here. Okay. Um, what that's going to do for you is you're going to have anion, 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 cation, cation, cation. Okay. And so you'll notice here that we have one, two, three, four, five negative charges, and we have one, two, three, four, five positive charges. So what we have in this case, when we throw sodium chloride in water, we have dissolved ions, but notice the solution is neutral. We aren't creating any charge. We're just producing species that are charged, but for every positive we have, we then have a corresponding negative. So it's still a neutral solution. But because that solution is composed of charges, we're going to then call that an electrolyte solution. Okay. So that's what an electrolyte solution is. You got to have dissolved ions in solution. Um, as another example, let's say, for example, we have sugar molecules. Okay. So the molecule for sugar is sucrose, and this is a model of what sucrose looks like. And what you might be able to see from here is there's a lot of red spheres sort of bonded to the white spheres. Those are all oxygen-hydrogen bonds. And the oxygen-hydrogen bonds are going to give more polar character to your molecule. And the more polar it's going to be, the better it's going to then dissolve in the water because, like we talked about here, polar molecule and polar molecule will like to interact and mix with one another. Okay? But you notice here, we have not created any charges. All we've done is we have just dissolved the molecule. And so since there's no charges, what we can say here is that we have a non-electrolyte solution. Okay, so we have dissolved the sucrose, but we don't have individual charges produced in the solution. And for that reason, since we don't have individual charges dissolved in solution, this is not going to conduct electricity, and therefore it's going to then be called a non-electrolyte solution. So in summary, if you have dissolved ions, it's going to be an electrolyte solution. If you have dissolved molecules, things that are themselves neutral, then you're going to have a non-electrolyte solution. So the definition for electrolyte solution, it can be either what's called a strong electrolyte solution, a weak electrolyte solution, or a non-electrolyte solution. What you notice here is that the strong electrolyte solution conducts electricity really well. You notice that the non-electrolyte solution does not conduct electricity. And then in the middle, you then see that then a weak electrolyte solution conducts some electricity, not tons really. Okay. And so at the molecular level of what we're viewing here, a strong electrolyte solution has many dissolved ions. Okay. You'll notice here in the weak electrolyte solution, we don't have as many ions as we did in the strong electrolyte solution. You're going to notice in the weak electrolyte solution, we only have one anion here and one cation. And so that is going to then be a weak electrolyte solution. There are some ions, but not that many. And then finally, you then have a non-electrolyte solution where you notice that there are going to be no ions, and so there's going to be no conducting of electricity. So that's how that's going to work for then our strong, weak, and non-electrolytes. Okay, so just to show you some examples of strong, weak, and non-electrolytes, usually strong acids are good examples of strong electrolytes. Strong bases are other good examples. Um, Weak electrolytes, that would be like acetic acid, hydrogen cyanide, and other weak acids. Some non-electrolytes would be water, methanol, and most other organic compounds. Memorizing this table is not important. We'll learn later how to determine whether or not something's going to dissolve well or mix well with water. Okay, so now we want to sort of go into our formal definition of a solution. Okay, so we've talked about solutions of water in the earlier part of this lecture. And so solutions are described as a homogeneous mixture of two or more substances. So in short, the solute is what's going to be called the minority component or the minority components. And then the majority component is going to then be called the solvent. Okay, so whatever you have the most of, that's the solvent. And then whatever else is dissolved in the solvent is going to then be the solute or solutes. So as a simple example, if you have water and you then dump in some salt, you are going to then have a salty water solution. And since in this case we have more water than the salt that we added in, we are going to have water be our solvent and then sodium chloride, our salt, being our solute. And together, the salt and the water make up the solution. So solvent plus solute equals solution. All right. One thing to point out to you is that solutions are not always in the liquid phase. So, for example, in our salty water example from the previous slide, water is in the liquid phase, or the solvent is in the liquid phase. That's not always true. And so this table does a nice job sort of showing that that's not the case all the time. So you can have gas phase solutions. So, for example, right now we are inhaling air in the gas phase. And air is it's going to be like 78-ish percent molecular nitrogen. It's going to be a good chunk of molecular oxygen. It's going to have some carbon dioxide in there. There'll be a little bit of methane in there. And so essentially our molecular nitrogen, which is, 78% of the air that we are breathing right now, that's going to be your solvent. And then the O2, the CH4, maybe a little bit of water in the atmosphere as well. Those are all going to then be the solutes because they're the minority components. So molecular nitrogen is going to be the solvent, and then all the other gases in the atmosphere, those are going to then be our solutes. So that's an example of a gas phase solution. You can also have then what's described as a liquid solution. And these are the ones that we most commonly encounter in chemistry context. And so what I want to investigate here is I have three examples where the solvent phase is the liquid, but the solute phase is going to either be a gas, a liquid, or a solid. So if we have a liquid solvent and a gas phase solute, an example of that would be soda water. So in soda water or carbonated water, you jam in CO2 into the water. And so the CO2 is going to be your solute, and then the water is going to then be your solvent. So that's an example of a liquid phase solution where a gas is the solute. We can also have examples of a liquid phase solution where a liquid is the solute. An example of that is the one we just talked about earlier today, which is going to be vodka. Vodka is about a 50-50 mixture of ethanol and water. So we'll just go for this example here. We'll say that we have a majority of water and then a minority component of vodka. And so in that case, we would then have water as the solvent, and then we'd have ethanol as the solute. Okay. Then what we can do is we can look at then the liquid phase solution when we then have a solid solute. And that's another one that we've looked at today, which is seawater. So seawater has water as the solvent, and then it has salt or sodium chloride as the solute. And so what we can see here is there are multiple examples of liquid phase solutions where we can either have the solute be a gas, a liquid, or a solid. Okay, so then the next thing that we can do here is we can also have solid phase solutions. So that might sound a little strange to you, but you can have solid phase solutions. So for example, like I play the trumpet, so a lot of trumpets are made out of brass, which is an alloy of copper and zinc. And so whatever element you have in the majority phase, that's going to then be the solvent. And whatever metal you have that's in the minority component, that's going to then be the solute. And so brass is itself a solution where the majority component is going to then be the solvent, and the minority component or components is going to then be the solute. Okay, so we've talked about solutions, we've defined them, we've talked about solute, we've talked about solvent, we've talked about the solution. And so one of the things that we're going to do now is talk about concentration units. Okay, so units for concentration, there's a large number of them, and they're convenient for particular cases, and that's why there's a lot of them. I'll tell you which one chemistry people tend to like the most, but we'll go through a number of the common ones. So, for example, concentration just tells you how much solute you have, the amount of solute per volume that you have. That's pretty much what concentration tells you. So there are a number of different concentration units. The first one is weight by volume percent, which tells you grams of solute per milliliters of solution times 100. You can have a volume by volume percent, which is milliliters of solute divided by milliliters of solution times 100. And then you can have this one here, which is called molarity. Molarity is described as mole of solute divided by liters of solution. And you can probably imagine, chemistry people, we love the mole. So our favorite unit of concentration is going to most likely then be molarity. Okay. One other thing I just want to point out to you is, if you ever get like a blood test, take a look at it and you can notice that for all the different components that they're measuring, um, these are common units that you'll maybe find in a blood test. And so here we have milligrams per deciliter. So deci is times 10 to the negative 1. And then you'll notice our friends that we've seen before from our SI prefixes. We have milligrams, micrograms, and nanograms. So in the health sphere that we have, those SI prefixes also show up a lot too. And so this is not every concentration unit that exists, but this covers a good chunk of them. And as chemists, we like the one molarity. Okay, so just to give you an example of sort of what we can do here. So a common saline solution for IVs is often prepared by dissolving 9 grams of salt, or 9 grams of sodium chloride, that is, in 1 liter of water. Calculate the concentration in molarity. And so to solve this question, you need to know that the density of water is going to be 1.00 grams per milliliter. So what we need to do is we need to then convert this amount of solute per solvent into mole per liter. And so what you'll notice here is when you do this question here, since it's 9 grams of salt per 1 liter of solution, if you then do your gram of solute per milliliter of solution, multiply by 100, you're going to then get 0.9%. So this is a 0.9% weight by volume solution. And here we're asking to then convert that into molarity. And so um, we know how many moles of sodium chloride we have because we know that we start off with 9 grams of sodium chloride. And so what you can do here is you can then have your moles of sodium chloride, and then you then have your volume of solution. Okay. And so how do we know how many moles of sodium chloride we have? Well, we know that we start off with 9.00 grams of sodium chloride. And you can see here, here's the 9 grams that we start with. As you can see, there's a small typo. That should say 9.00 grams to get the sig figs to be consistent. And so you then use the mass of sodium chloride, and then you look up the molar mass for sodium chloride to get into moles of sodium chloride. And when you do that, you're going to then get moles of sodium chloride. Now we have that numerator done, and now we want to then move on to the into the denominator, which is the volume of solution. And that volume of the solution is going to then be 1 liter. And so that 1 liter then goes down here. And then what unit are we left with? Well, we notice none of the units are going to cancel. And so we're left with mole per liter, and then we get our unit of mole per liter. And one thing just to point out to you is that the unit mole per liter is what's called molarity. And oftentimes that'll then be written as a capital M. And so you'll notice sometimes molarity written like this, and sometimes you'll then see it written like this. Okay. One other thing I wanted to emphasize here, when you are using the definition of molarity, it's mole of solute divided by liters of solution. So the key thing here is you got to figure out whatever your volume of your solution is and then convert it into liters. And then when you have mole of solute per the volume of solution in liters, that ratio is going to then be what's called your molarity. Okay, one thing to point out to you is if you are given the volume of your solution and you are then given then the molarity of your solution, you can then figure out then how many moles of solute you're going to have. So just to show you here, Liters times molarity is the same thing as liters of solution times moles of solution per liters of solution. So what we have here is liters of solution. This is an equation here. Liters of solution is here on the left-hand side. Liters of solution is here on the right-hand side. Here we have molarity on the left-hand side. And here we have moles of solute per liters of solution. Well, that's the same thing as molarity. So this thing up here is going to be the molarity. And when you write the molarity like this, what you can notice is the liters of solution and the liters of solution will cancel, and then you'll be left with now moles of solute. And so you now will have moles of solute is equal to molarity times liters of solution. And if we write that a little bit differently, you're going to see moles of solute is equal to liters of solution times the molarity. So if I know what volume of my solution is in liters, and I know its concentration in molarity, I can then calculate however many moles of solute I have. So that's one important thing to point out to you. Okay, so here's sort of a health example that we can look at. So typical blood serum is about 0.14 molar sodium chloride. What volume of blood contains 1 milligram of sodium chloride? Okay. So the key thing to point out here is we're asked to say, okay, well, what volume of blood is going to contain 1 milligram of sodium chloride? So I'm asking us to solve for a volume here, which means volume is just 1 unit. So that means I need to then start with 1 unit to then end with 1 unit. So what that tells me is I'm going to start with the 1 milligram of sodium chloride because that is 1 unit. The 0.14 molar sodium chloride, that is actually, remember, a ratio of units because molar sodium chloride means I have 0.14 mole of sodium chloride per 1 liter of solution. So this is a ratio or a conversion factor, and then this is just going to be 1 unit. And so the way you solve the question is you start off within your let's see here. You're going to start off with your 1 milligram of sodium chloride. And so here you have your 1 milligram of sodium chloride. You then use the molar mass to go from grams of sodium chloride into moles of sodium chloride. And then if you then divide by then the volume by doing this, or sorry, if you then let's give this a moment here. So you're gonna go from grams into moles of sodium chloride. So then once you know the moles of sodium chloride, then you can use the concentration of the sodium chloride, which is going to be 0.14 mole of sodium chloride per liter of solution. You can then say I have 0.14 mole of sodium chloride per 1 liter of solution. Then the mole and the mole will cancel each other out, then leaving you now within a final answer in liters. So just to sort of recap here, you start with your 1 milligram of sodium chloride. You use the molar mass of sodium chloride to pivot out of grams of sodium chloride and into moles of sodium chloride. You're given the concentration, which is a mole per liter ratio. And so you can then use that molarity as a conversion factor that lets you then pivot out of moles of sodium chloride and into then liters of solution. And so when you do that, you're going to then get an answer of 1.2 times 10 to the negative 4 liters. So that's going to then be the volume that contains 1 milligram of sodium chloride. All right, another thing that's worth talking about is dilution. Chemistry dilution is important because oftentimes what we're dealing with are very dilute solutions. And so, as you can imagine, concentrated solutions have more solute in them per volume, and then more diluted solutions are going to then have less solute per volume. So, I'll start with an example of maybe you make some Kool-Aid, okay? You make some Kool-Aid and you pour the powder in, you add some water, and then you then get this concentrated solution of Kool-Aid. What you can then do is, let's say hypothetically, so let's say this is 100 milliliters of Kool-Aid, okay? Let's say you instead then take 10 milliliters of this, and then you dump it into 90 milliliters of just pure water. So what you're going to do here is you're going to then take 10 milliliters of this, dump it into then 90 milliliters of water, and then what's going to happen is you're going to then get a diluted solution. And so that's why it then looks less red here. So you're going to take 10 mils of this, pour it into an empty cup, and then add 90 milliliters of water, get to that 100 milliliter total volume. But now you have essentially 1/10 the amount of the Kool-Aid for your concentration. So you've done what's called a 1 to 10 dilution. You diluted by a factor of 10 going from here to here. Then, if you then take up 10 milliliters of this one, dump it into an empty glass, and then add 90 milliliters of water, mix it up, then you get this solution. And then, if you then take 10 milliliters of this solution, dump it into an empty container, dump in 90 milliliters of water, now you have then this solution. And then lastly, if you were to then take 10 milliliters of this solution, dump it into an empty glass, pour in 90 milliliters of water, get 100 milliliters in total volume, you would then have this solution. And so what we have shown here is what's called a serial dilution. So we're not talking about the cereal that you dilute with your milk. We're talking about cereal as in a series. And so this is factor of 10 more concentrated than this one. This is factor of 10 more concentrated than this one. And then this one is a factor of 10 more concentrated than this one. And then this one is a factor of 10 more concentrated than this one. So as we go from here to here to here to here to here, we go up in concentration by a factor of 10, 10, 10, and 10. And so that's essentially what a dilution is. And so you can have something be diluted by adding more solvent. If you keep the amount of solute the same, but then add more solvent, you're going to then get a diluted solution. And so there's an equation that is commonly used when doing dilutions, and it's called M1V1 equals M2V2. Okay. Um, I'm using the symbols M because often in chemistry, the unit of concentration you're going to use is going to then be molarity. But technically, I guess a better equation for this would be C1V1 equals C2V2, where the lowercase c is going to correspond to the concentration. But most people just go with this equation. Either one will work. But when you do this equation, is what allows you to do all the types of dilutions that you might be interested in. And so M1 is your starting concentration, and then M2 is going to then be your final concentration. And then V1 is going to be the volume you start with, and then V2 is going to then be the volume that you end with. So I have some notes here for us all. So if we are talking about a dilution, we are diluting a solution. M1 is going to be the higher concentration, and then M2 is going to then be the lower concentration because we're diluting solution 1 to then have concentration of M2. V1 is the starting volume, so that's going to be some smaller number. And then if we're doing a dilution, we're going to then add more volume. And so then the volume we end with is going to be larger. So in the context of dilution, V2 is going to then be bigger than V1. And M1 is going to then be lower than, and then M1 is going to then be higher than M2. So when you do a dilution, you're going to go from high concentration to low concentration. And when you do a dilution, you're going to start from a lower volume to then a greater volume. And that's all sort of wrapped up in this equation here. And so since this is an algebraic equation, we have one equation, which means we can then solve for one unknown. And so what this practically means for us is if I know 3 of the 4 terms, I can then solve for the remaining one. So as an example to sort of show you what this can look like, Here we have a volume of 16 molar sulfuric acid. So that we're asking what volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.10 molar sulfuric acid solution. So here we're asking to solve for then a volume. And so when you're doing this question, you need to figure out of the terms that you're given, what do they correspond to? And another thing that you need to do is you need to ask yourself, well, what type of question am I asking to solve here? And so notice that you're given information about concentration, concentration information, and then you're given volume information. So that's going to indicate that probably you're going to be doing a M1V1 equals M2V2 calculation. And so to do it, you then take your M1V1 equals M2V2. And then what you want to do is you want to figure out, well, what you're solving for. And so they're saying what volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of 0.10 molar sulfuric acid. So it's what volume must I start with to then dilute it down to zero point 0.1 molar and have a total volume of 1.5 liters. So in this case, what this means is I need to solve for V1. What volume must I have to dilute? And so then using algebra, you can then get M2 V2 divided by M1 is equal to V1. So the way I went from here to here is I divide both sides by M1. So M1 over here cancels. And then I then get the M2 V2 over M1. And then once you got the equation out, then you plug in the numbers as they are. So M2 is going to be the diluted concentration. So the diluted concentration we can see here is 0.10 molar. So the 0.10 molar goes there. Um, V2 is going to be the total volume of my diluted solution. And so we can see here, it's going to then be 1.5 liters. And so the 1.5 liters goes in here. And then lastly, we need our M1, which is our starting concentration before we do the dilution. And so we can go here and see that the concentration of the sulfuric acid prior to dilution is going to then be 16 molar. And so we do that. And here's our equation. We plug in the values. We add our units. Keep in mind, you want to add your units. And you'll notice that then when we plug all the numbers in, we get this expression. And you'll notice that molarity and molarity will cancel, leaving us with then liters as our units. And when you do that, that's going to correspond to 9.4 times 10 to the negative 3 liters. And then since 10 to negative 3 is milli, we can then clean it up a little bit and write our volume as 9.4 milliliters. So in other words, what this tells us is I need to take 9.4 milliliters of my 16 molar sulfuric acid solution. And if I dilute it down to 1.5 liters, then my solution is going to have a concentration of 0.10 molar. So essentially, these questions requires you to one, identify what type of question it is. And so usually you will be given a large amount of information, which is going to probably suggest you're going to use this equation. You then need to figure out what you have and what you don't have. And then for what you don't have, you need to then by algebra solve symbolically for it. And then after that, you then plug in the different terms for where they belong, make sure the units you're being good about, and then after that, then you'll get your final answer. And so that's essentially how the dilution question is going to work. Okay, so next thing we're going to talk about. So we've talked about solutions. We've talked about what they are conceptually. We've talked about solute, solvent, solution. We've talked about different concentrations of solutions. So now what we're going to do is we are going to then describe three main types of reactions. So first, we're going to talk about precipitation reactions. Then we'll then move on to acid-base reactions. And then finally, we'll then work on oxidation, reduction, or redox reactions. And that's going to be sort of near the end of this total chapter that we're going to be dealing with. And so precipitation reactions, we'll give some time talking about those today. We'll give an introduction to acid-base reactions, but in Chem 3B, we'll have a full chapter or more on acids and bases. And then also in Chemistry 3B, we'll have another chapter dedicated to oxidation and reduction reactions. So that's sort of the overview of where we're going. So where we're going to go today is we'll cover precipitation reactions, and then we'll then likely either leave one question of precipitation reactions for the end, or we'll get it all the way through and we'll cut it off before we get to acid and base reactions. All right, so as a refresher, water solubility. So we know that sodium chloride is going to then be dissolved in water. We know this from our daily lives. You add salt to water, it dissolves really easily. So sodium chloride has a really high solubility in water. Well, another ionic compound is the solid silver chloride. If you add silver chloride to water, what you're going to notice is actually it's not going to dissolve. And so you're going to have no solubility of silver chloride in water. So it's a more involved question to answer why silver chloride doesn't dissolve compared to sodium chloride. But in our introductory class here, we're going to then be able just to use a table to then identify whether or not a ionic compound will dissolve in water or not in water. And so based on this, we can just say sodium chloride does dissolve in water, and we can say that silver chloride does not dissolve in water. So a really classic and very visual example of a precipitation reaction is this one. So here we have a solution of potassium iodide, and then we're then going to be adding it to then a solution of lead nitrate. And what that's going to do for you is it's going to then produce lead iodide and then potassium nitrate. Okay. So sort of show you what's going on here. Here we have so the colorless solution here. Okay. This is going to then be lead nitrate solution. Then what we're going to do is we're going to then get some sort of piece of glassware, maybe a burette, and then we're going to add potassium iodide in. So potassium iodide you can see is colorless. Lead nitrate is colorless. But upon mixing the potassium iodide with the lead nitrate, you then get this lovely yellow color. That yellow color is going to then be the production of lead iodide. And that's going to be what's called a precipitate. And you'll notice that it has its phase of matter, which is a solid. Since it's a solid, it doesn't get dissolved by the water. And so that's what we're seeing here. And then we're also going to prepare some potassium nitrate, but that is fully dissolved in the water, and so we're not going to see any of that. And so this is an example of a precipitation reaction, which is where you start off with something that's a solution, and then you then produce something that is not soluble in that solution. So the key thing here is that lead iodide is not soluble in water, and lead iodide has a yellow color, so it's more visual, and so we can see it. And so this is an example of a precipitation reaction. Okay. The reason we see the lead iodide is because it does not get dissolved, but it exists as a solid. Okay. And so it's going to then eventually settle down to then the bottom of the glass container, and it's not going to get dissolved. Okay, so just to sort of show you a little bit from a cartoon example of what this is going to look like. If you start with potassium, let's see here. If you start with potassium iodide, which is this, you have K plus ions and I minus ions in solution. If you start with lead nitrate solution, you have lead cation and nitrate anions in solution. And so those are both going to be fully dissolved. And so that's why they're aqueous solutions. So here we have our aqueous potassium iodide, which is this one. And then down here we have our aqueous lead nitrate, which is going to then be this one. However, when we then dump the two into the same container together, now we're going to have potassium and let's see, potassium, and we're gonna have lead, cation, and then we're gonna then have iodide anion and nitrate anion. Okay. And so what that's going to do for us is now we have all those ions sort of in the same solution, in the same mixture together. And what's going to happen is the original compounds that we have are going to essentially swap partners. So what that means here is the K plus from potassium iodide is then going to then partner up with then the nitrate of lead nitrate, and you're going to then form potassium nitrate. And that is going to be what you have here. Then the lead cation is going to swap out its partner for then the iodide anion, forming then lead iodide. And so then that's going to then be the other new partner that we have. And so the thing to consider here is these are the new products that we could be making, and they potentially may be insoluble in water. And so to determine whether they are insoluble or soluble in water, we need to then use something called a solubility table. Okay. And so this is the solubility table. It's something that you're expected to know how to use, but it's not something you're expected to have memorized. This table will be given to you on the exam if you're asked any question that requires you to do something like this. Okay. So the way the solubility table works is it says in the top half, compounds containing the following ions are mostly soluble. So if you have lithium cation, sodium cation, etc., um, the following ion is going to then be soluble. So what this means here is there are going to be no exceptions. So if compounds contain any of those as the cations, then it's going to then be soluble in water. Then if you then go down to here, here you have some anions. If you have any of these, what this is going to tell you is that there are some exceptions. So when any of these ions pair with silver, mercury, or lead, the compound is insoluble. So what it essentially works here is on the left-hand side, it's going to describe things as being soluble, but if there's an exception, then it's going to then now be something that's insoluble. And then the bottom part of the table works differently. It essentially says anything with this and this are going to be insoluble. However, if it pairs with this, or this, then it is going to be soluble. And likewise, these carbonate and phosphate, those will in general be insoluble when they form compounds, except when they are mixed with, lithium cation, sodium cation, potassium cation, and ammonium cation. In that case, then it will be soluble. So that's the table in a nutshell. The best way to sort of explain it is to show it in an example. So, um, for example, we had in our earlier question sodium nitrate. Okay, so we know that let's go here. So let's go to our let's go to here to our example. So yeah, so this is just an example to show you here. So the question is sodium nitrate soluble in water? And so what we can do here is we look up like, okay, well, we have Na plus, and then the anion is going to be nitrate. Okay. If we have Na plus, there are no exceptions. And so what that means is sodium nitrate is going to then be soluble in water. So that's an example of what we have here. So if you have sodium nitrate, or for example, sodium chloride, there's no exceptions that you're going to have as long as you have the sodium cation. And so everything with the sodium cation is going to then be soluble. So that's our first example. What we can take a look here is let's ask now if lead iodide is soluble in water. And so what you notice here is if we go down here, here we find iodide, and then we see that when any of these ions are paired with the iodide, the compound is insoluble. And so you notice that here we have lead, which is an exception. So since we have lead with iodide, that means it's going to then be insoluble. And that's what we have here, which is our lead iodide right here. This is our insoluble lead iodide. So that's how we can use the table to then determine that lead iodide is then insoluble in water. Okay. Okay, so next thing we need to do is we need to be able to describe a reaction in solution. Okay, so what's this going to look like? So we can have a few different sort of things to write out. And so the first one is going to be what's called the formula equation. Okay, so here we are going to say, here we have potassium hydroxide reacting with iron nitrate, and that's going to then give you iron hydroxide and potassium nitrate. This is what's called then the formula equation. It tells you that, this aqueous solution reacts with this aqueous solution. It's going to form a precipitate of iron hydroxide, and then it's going to then also form some potassium nitrate. Let's double check though. Let's prove here why this is insoluble. So let's look up iron hydroxide in the previous table here. So if we look up iron hydroxide, we notice here that here we have hydroxide, and it says that compounds containing the following ions are mostly insoluble. So we have hydroxide, okay? And then the counter ion for that is going to be iron. And does iron show up as an exception? We notice that iron does not show up as an exception. So therefore, it's not going to be soluble, which means that it's anything with the iron hydroxide is going to then be insoluble in water. Okay, so we have hydroxide here. The iron does not show up as an exception. And so therefore, we are going to then have our ionic compound then be insoluble in water. And that's what we have here written as iron hydroxide in the solid state. Okay, so that's the formula equation. You can then have what's called the complete ionic equation. What that means is these are ions in solution. And so if you break them up into the ions that they are, that is what you then call the complete ionic equation. So what this means is you need to be able to look at an ionic compound and be able to separate it into its component ions. That's a key skill that you want to be able to apply here. And so really knowing how to do this requires that you know well the charges and the formulas of different ions and different polyatomic ions. So that's why that one table from a couple of lectures ago is important to then having it be memorized. So we know that K plus or potassium is in the first column of the periodic table. So it's going to then be K plus. We know that hydroxide has a charge of -1. And because we have 3K OH, what that means is we have 3K pluses and 3 OH minuses. So this 3K OH turns into this and this. We know that nitrate is going to have a charge of -1. And we know that there's going to be three of them. And so it's going to then be 3 NO3 minus. We notice there's only one iron per the three nitrates. So that means iron has to have a charge of +3. So we say that we start off with 3 NO3 minuses, which means we have to then have one iron plus. So that covers then this part. Here we know we have three hydroxides, which are going to have a charge of -1. And then we see here that we then have iron. So it's going to then be iron 3 hydroxide. But look at this. You'll notice that it gets written the same way in the complete ionic equation. So we know this is iron 3 with 3 OH minuses, but we write it as written in the chemical equation because it's not an aqueous species. It exists together as a solid. So actually, you can leave that one just alone. When we then go on to then potassium nitrate, which is an aqueous solution, we know that we have three potassium nitrates, and so that means 3K pluses and 3 NO3 minuses. So because we know potassium cation is going to be K plus, and we know nitrate anion is going to be minus. We know that if we're going to have the one-to-one ratio of K plus to NO3 minus. And so since we have three of it here, it's going to be 3K plus and 3 NO3 minus. So in summary, the way this works is you need to at minimum know what the charge of one of the other ions is going to be. If you know what the charge of the other ion of one of the ions, you can then figure out based on the amount or the ratio of ion to ion what then the charge for then the other ion is going to be. Okay. So that's sort of how that's going to work. So that's going to be a skill that'll take a little bit of time to develop, but just make sure to sort of spend some time looking with the table of common polyatomic ions, and then you can then know that it's going to be K plus and OH minus, NO3 minus with then Fe3 plus. We can skip this one, and then knowing that nitrate is NO3 minus, or knowing that K is K plus. So you just need to know half of it, and you can then deduce what the other one's going to be because you have the full formula. All right, so that's what's called then the complete ionic equation. So the traditional equation that we look at is what's called the formula equation. And then when we split everything up into the individual ions, that's what's then called the complete ionic equation. Then what we can do is, and let's take a look here. Okay, there you go. So then what you can do is you can do the following. So you'll notice that if that we have 3K plus on the left-hand side, and we also have 3K plus on the right-hand side. So it shows up on the left-hand side, shows up on the right-hand side. What that means is we can cancel the two of those terms out from our equation because nothing's happened. It started there and it ended there. So we can just ignore it because it's not participating in any of the chemistry. Because it's not participating in the chemistry, we call it a spectator ion. So we can cross out the 3K plus and the 3K plus. And we can also do the same thing with the three nitrates. Here we have three nitrates on the left-hand side, and here we have three nitrates on the right-hand side. So in summary, we can cancel out the three potassiums, and we can then cancel out the three nitrates. Once we cancel those out, then our complete ionic equation is going to then reduce down to something simpler. And that thing that is simpler is what's then called the net ionic equation. And what you notice is this is what the actual chemistry occurs. You get three hydroxides with one iron 3 plus cation, and you then form iron 3 hydroxide. And that is going to then be an insoluble precipitate. And so that's then where then the solid is going to come from. Okay, so this is the next question that I think we'll look at. And what I am thinking here is this is probably one that would be good to go over in person. So we'll save this question for then the start of our next class. So thank you for watching and have a great rest of your day. Thank you.